So today I'm going to talk about how to do diffraction and interference problems. So we'll start by a quick description of what diffraction is. Diffraction is a change in the shape of a wave due to the presence of a barrier. So if you look at the pictures A, B, and C, you can see in those pictures the size of the barrier is gradually getting smaller, and as the size of the barrier gets smaller, the wave that's incident from the left side as a straight line, a plane wave, gets more and more bent as it comes out the other side. So the narrower the hole in the barrier, the more the wave is going to bend or diffract. And it also depends on the wavelength compared to the opening. So the larger the value of the wavelength divided by the size of the opening, the more the light will bend. Since light is diffracted through openings, we can say that light is a wave. Another thing that we learned was that light gets refracted when it enters media in which the speed of light is different. In other words, it has a different index of refraction. And we saw that when we went, as shown in the picture above, from a low index of refraction to a higher index of refraction, the ray of light bent towards the normal to the surface. So if we look at this picture, what's a ray and what's a wavefront? Well, a ray is basically an arrow, like that pink arrow, that's perpendicular to the wavefront. So if you look at point B, you can see it's perpendicular to the wavefront. So basically it points the direction that the light wave is going. And so when we did all our optics for mirrors and lenses, we just assumed that light was a ray and we ignored the fact that it was a wave. So light is a wave. It has, as we said, for electromagnetic waves, it's got peaks and valleys in the electric field and magnetic field. And a wave front is a line that joins points that have a similar phase. So for example, it could be through all the peaks in the waves. The distance between the wave fronts is the wavelength. So we have, if you look in the two different media, we have two different wavelengths in the two different materials. So what's happening, one way to think about it is that if you imagine that you have a whole line of soldiers walking along each of these wavefronts, so these are columns of soldiers walking along, and eventually the soldiers are walking on in the white part, assume they're walking on concrete, and then they enter some mud. So when they enter some mud, they're going to slow down, and so then that wave front is going to bend slightly as the soldiers enter. As the wave goes further and further, more and more of the wave front is bent. And so that means that the line perpendicular to that wave front also bends. And it bends towards the normal, to the interface between the concrete and the mud in this case. If you look at the wavelengths, the distance between the two columns of soldiers is equal to the speed they're going times the time distance between them. So you can see that the wavelength when they're walking faster is going to be bigger than the wavelength when they're walking slower. So that's sort of a good analogy of what's happening with light. So since the waves are slower in the higher index of refraction materials, the wavefront bends, the wavelength gets shorter as it slows down, but the frequency, the time interval, if someone's standing here with a stopwatch measuring the time between when the columns of soldiers march by and someone else is doing that out on the concrete, you'll measure the same period, the same time between them. So the frequency is the same, the wavelength changes, and the amount that the wavelength changes by is just the index of refraction. So the wavelength in a vacuum, where n equals 1, divided by the index of refraction of the material, will give you the new wavelength. Okay, let's just do a quick review of interference. So if you have two waves that are exactly in phase, so if you look at the picture A, the peaks line up and the troughs line up. When those two waves meet, their amplitudes just add up, and you get what we call constructive interference. You get a wave that's twice as tall. If they're 180 degrees out of phase, then one of them has a peak when the other one has a trough. And if we add those up together, we always have a positive and a negative of the same size, and they completely destroy each other. So that's destructive interference. And usually in real life, what we get is something in between the two, partially constructive or partially destructive. All right, so Now we get on to Young's double slit experiment. So if we have the light that's incident from the left and it hits two different openings. So what's going to happen is when the light hits each opening, it's going to start to curve out, as you can see in the figure. And those light rays will travel perpendicular to the wavefront, so you can get different light rays traveling out from them. And as these light waves cross each other, they're going to interfere with each other. And so on that screen, there's going to be an interference pattern. And it's important when we do this that the sources are coherent. In other words, the light is in phase. So typically what's done is you have one single source of light that these plane waves come out of. And so when they hit the barriers, they both have the same phase initially. All right, so let's look at some pictures of what happens. So if we look at the light waves that come from each slit and hit right at the center of the screen, you can see that as they go along, they travel, each of them travels the same distance, so they're still going to be in phase when they hit the screen. And so we're going to get a bright spot at the center of the screen. As we change the angle, the path length traveled by the light ray from slit 1 and from slit 2 is going to be different. And the extra distance is essentially going to be the short side of that triangle that's shown in there. So for a point on the screen that's at an angle theta from the center of the screen, that distance there is going to be d times sine theta. So for that little triangle, right angle triangle, where this is theta, and this side here is d, that is d sine theta. Okay, so if the path length difference is equal to 0, or 1 wavelength, or 2 wavelengths, or 3 wavelengths exactly, then the waves will be in phase when they hit the screen, and we'll get a bright spot, or constructive interference. If they're out by half a wavelength, as shown in figure C, then one of them is going to have a peak, the other one's going to have a trough, and they'll add up to 0, and we'll get a dark spot on the screen. So the path length difference, as shown in figure D, at the far right, path length difference d sine theta, if it's equal to m, an integer, times lambda, we will get a bright spot. If it's equal to m plus a half, so half a wavelength, 1.5 wavelengths, 2.5 wavelengths, etc., then we'll get a dark spot. So we're going to get an alternating pattern of light and dark spots on the screen. So this is essentially what the screen would look like if we plotted the brightness of the wave on the y-axis and the distance along the screen on the x-axis. So at the very center, where m equals 0, we're going to have a peak. Then we're going to go out either to the left or to the right. We're going to go down to a valley where we have a dark spot. So this is for m equals 0, each of them, for a dark spot. Then we're going to go back up. We're going to get a bright spot on each side for m equals 1. So it's symmetric. It's not quite as high as the center peak. And as we go further and further out, we're going to get a symmetrical pattern of light and dark peaks with the amplitude gradually decreasing. Okay, now the peak position, remember, where the peak is depends on m lambda. So it depends on the wavelength. So different wavelengths are going to have peaks at different points. So if we shine on white light, which is a combination of all the different colors of light, then the wavelengths will separate out at m equals 1 and m equals 2. And so what we'll see is a rainbow that's symmetric about the center. Often we ask in a question, what is the distance from the center line that a peak occurs? Or you might be told the distance from the center line on the screen where the peak occurs. So that's the distance y in the figure below. So if you have the screen a distance L away, then y is going to be, if we look at our triangle, we know L, we know theta, so y over L is equal to tan theta, opposite over adjacent, so y is equal to L tan theta. If the angle's small enough then tan theta is approximately equal to sine theta. And if the angle is really small enough, then remember we have d sine theta equals m lambda. So for small enough angles, sine theta, actually I guess it's true for any angle, isn't it? Sine theta is equal to m lambda over d. So y is equal to L times m lambda over d if the angle is small enough that you can assume that tan theta and sine theta are the same. Usually it's safest to assume that it's not and make sure you get exactly the right answer. Okay, so let's quickly do a question. So typical question is, tells you the slit separation. So light hits two slits that are 0.042 millimeters apart. Okay, so that's our slit separation, 0.042 millimeters. So we need to divide that by 1,000 to convert it into meters. So that is 4.2 times 10 to the minus 5 meters. Projected onto a screen 5 meters away. So that's the distance to the screen. That's what we're calling L. The fifth order bright fringe, so that means m equals 5, is at 68.5 centimeters from the center of the diffraction pattern. So m, so that's y, is equal to 68.5 centimeters or 0.685 meters. And they're saying, what is the wavelength of the light? So I want to find lambda. So what are our equations? Our equations are y is equal to L tan theta, and d sine theta is either equal to m lambda if it's bright, or m plus a half lambda if it's a dark fringe. We're told it's bright, so we're going to say equal to m lambda. All right, so what do we know? Well, we know our y, we know L, we don't know theta, we know d, and we know m, and we're trying to find lambda. Okay, so we don't know theta, but we could use the equation on the left to give us theta, and then given theta, then we could rearrange the second equation to find lambda. All right, so let's use this first equation. Tan theta is y over L. So that's 0.685 meters divided by 5 meters, or 0.137. There's no units because meters divided by meters canceled out. So to give me my theta, I'm going to do inverse tan of 0.137. So theta is equal to 7.8 degrees. So that's probably a small enough angle that we could have used the sine theta tan theta approximation. All right, so now I know my theta. I can take that theta and plug it back in to that equation to give me lambda. So if I rearrange it, I've got d sine theta equals m lambda. So lambda is equal to d sine theta over m. So now I just plug in my numbers. So d, 4.2 times 10 to the minus 5 times the sine of 7.8 degrees. Make sure your calculator's in degrees and not radians. Divide by m, which is 5. And I get my wavelength is 1.14 times 10 to the minus 6. Remember, wavelength is a distance, so that is meters. Okay, another typical kind of problem would be to give you the wavelength and the slit separation and ask you how far apart on the screen are the fringes. So ask you to find y, or it might give you y and lambda and ask you to find d. So what you're going to do is you're just going to play with these two equations, figure out what it is you're given, and then rearrange to find what you need to find for the problem. All right, what if I have a single slit? Can I also get diffraction? Well, yes, I can, because if I have an obstacle or a single slit, light coming from either side of that slit will also be bent, and when those two rays meet, they'll interfere with each other. So when we have a single slit, what we get is we get a single broad peak in the center, and the position of the minimum is where d sine theta, where d is the slit width now, is equal to m lambda. So if the size of the slit is a lot less than the wavelength, then the wave is going to spread out a lot. If the slit width is a lot bigger than the wavelength, then there's going to be little bending of the light. So if you have a light wave which has a very small wavelength going through a window, there's going to be very little diffraction. But if you have it going through a very narrow slit, like maybe the width of a hair, then it will bend out a lot. So the position of the minima in the diffraction pattern are given by d sine theta equals m lambda. And if you look at the pattern here, you can see that the secondary peaks on the sides are much, much shorter than what you saw in the double slit pattern. What happens if we put in more slits? So if we go to 3 or 5 or 1,000 slits, well, we get what's called a diffraction grating. So if you have a large number of equally spaced narrow slits or narrow lines, so it could be a piece of glass with a whole bunch of lines drawn on it that don't let the light through, we call it a transmission grating if it has slits to let the light through, so the light gets transmitted, or it's a reflection grating if it has lines on it that reflect the light. So it turns out that the more lines that you put in there, the more slits, the narrower the peaks are. So you go from a picture like an A to a picture like an B, where you have peaks. You notice the position of the peaks is the same because that's given by, again, d sine theta equals m lambda. So if you have the slit spacing the same, then the peaks are going to be at the same angle for a given wavelength, but the intermediate peaks get smaller. So the peaks get narrower, and these intermediate peaks get smaller. So here's a picture showing some diffraction grating pictures in figure A, where you have white light, a combination of red and blue light, at the center for m equals 0 because they both get diffracted to the same position there. And then as you go out to higher orders of m equals 1 and m equals 2, you can see the distance between the red and the blue line gets bigger. If you shine on real white light that has like a whole rainbow of colors in it, then you'll see you get a rainbow that spreads out again as m gets bigger. The width of that rainbow gets bigger and the brightness of it decreases. All right, so here's the problem that I want you to work on today. I give you the wavelength of the light. I give you the slit separation for a double slit experiment, and I give you the screen position, and I ask you to find the position of y for the m equals 0 and m equals 1 bright fringes, also for the dark fringes, and then what's the spacing between the two bright fringes on the screen.